In 2019, the world saw just over 100 rocket launches. 5 years later, in 2024, that number had nearly tripled to 258. And if current projections hold, by 2030, we could be looking at more than 2,000 launches each year. Humanity's space ambitions are accelerating at a breathtaking pace. Mega constellations of satellites are reshaping the night sky. Private companies are racing to deploy spacecraft faster and cheaper than ever before, and governments are investing in new exploration missions. But behind the awe-inspiring images of rocket plumes and spacecraft drifting into orbit lies a quieter, more sobering question. What is all this activity doing to the ozone layer? The fragile shield that protects life on Earth from harmful ultraviolet radiation. The ozone layer sits high above us in the stratosphere, between 15 and 50 kilometers up. There, a thin band of ozone molecules absorbs most of the sun's ultraviolet B rays, the ones that can cause skin cancer, cataracts, and DNA damage in living organisms. Thanks to the Montreal Protocol, the landmark treaty signed in 1987 that banned ozone-depleting chemicals like CFCs, the ozone layer has been slowly healing. The latest assessments suggest it could return to 1980 levels by around 2040 in most of the world, by 2045 over the Arctic, and by 2066 over Antarctica. But recovery is not yet complete. Global average ozone is still about 2% thinner than before industrial times, and now rockets are emerging as a new complication. For decades, scientists thought rocket emissions were too small to matter globally. After all, compared to factories, cars, and power plants, rocket launches seemed rare. But as the launch rate climbs, that assumption is being overturned. A 2025 study led by Revell and colleagues used one of the most advanced chemistry climate models available, known as Sukhodolov, to test what could happen if launches keep scaling up. Their scenarios looked ahead to 2030. In a conservative growth pathway with about 884 launches a year, the model showed a global average ozone decrease of about 0.17%. In a high-growth scenario, with 2,040 launches annually, the loss grew to 0.29% globally and up to nearly 4% over Antarctica in spring. At first glance, those numbers might seem small, but context matters. A 1% drop in ozone can lead to about a 1.2% increase in UV radiation at Earth's surface. And since the ozone layer is already weakened, even small setbacks could delay its recovery by years or even decades. So what exactly is happening in the stratosphere? The chemistry is complex but fascinating. First, solid rocket motors, which use ammonium perchlorate as an oxidizer, emit large amounts of hydrogen chloride gas and alumina particles. These substances climb into the stratosphere, where the particles act like chemical surfaces, triggering reactions that turn harmless chlorine compounds into highly reactive chlorine radicals. When sunlight hits, those radicals break apart ozone molecules over and over in a catalytic cycle. This is the same type of chemistry that once produced the Antarctic ozone hole in the CFC era. Second, there's soot. Hydrocarbon-fueled rockets, those burning kerosene, RP-1, or even some methane systems, inject black carbon particles directly into the upper atmosphere. Unlike soot from ground-level combustion, which washes out with rain, these particles can stay aloft for years. They absorb sunlight, heating their surroundings, which speeds up ozone-depleting chemical reactions. Modeling studies show that the soot from just a handful of heavy launches can have a measurable warming effect on the stratosphere, especially in the northern hemisphere, where most launches occur. And then there's re-entry, a piece of the puzzle scientists are only beginning to understand. When satellites and rocket stages plunge back through the atmosphere at the end of their life, they burn up. The extreme heating generates nitrogen oxides, which are themselves ozone destroyers. It also vaporizes metals from spacecraft alloys, aluminum, copper, lithium, even rare metals like niobium and hafnium. Recent flights over the United States detected these metallic fingerprints in about 10% of the sulfate particles in the stratosphere. Metals can alter the formation of clouds or provide new chemical surfaces for ozone destruction. And with tens of thousands of new satellites planned, these re-entry effects are likely to become more significant in the years ahead. Not all rockets are equally damaging. Solid rocket motors are the worst offenders for ozone because of their chlorine emissions. Kerosene-fueled rockets are major soot producers. Methane burns cleaner, producing less soot, though not zero. Hydrogen, paired with liquid oxygen, is by far the cleanest option in terms of ozone impact. Hydrogen engines emit water vapor, which can influence high-altitude cloudiness, but they don't produce chlorine or soot. The problem is that hydrogen is difficult to handle. It requires cryogenic temperatures, specialized infrastructure, and more complex engine designs. As a result, only about 6% of launches today use hydrogen. So what does a 0.29% ozone loss actually mean for us on the ground? On average, it could translate to about 1/3% more ultraviolet radiation globally. That might sound trivial, but over decades, and layered onto an ozone layer that is already 2% thinner than before, it adds up. The bigger risk is at the poles, where seasonal losses can spike several percent in just a few weeks, amplifying the Antarctic ozone hole just when recovery is finally within reach. Importantly, the study didn't even account for re-entry chemistry, meaning the real impacts are almost certainly larger. And that's before we factor in uncertainties in soot emissions from new methane engines or the complex interactions between metal particles, polar clouds, and ozone chemistry. In other words, the warning signs are flashing, but the numbers we have may be conservative. The good news is that the problem is solvable. The Montreal Protocol showed that global cooperation can heal the ozone layer. We can apply similar foresight here. That means shifting away from solid boosters where possible, designing hydrocarbon engines to minimize soot, and moving toward cleaner fuels like hydrogen. It means treating re-entry as a genuine emission source, tracking how much material is ablated, and possibly rethinking how satellites are disposed of. It also means monitoring rocket emissions the way we monitor power plants and aircraft, with real-time reporting and atmospheric sampling. At present, rocket emissions aren't regulated under the Montreal Protocol because the treaty was designed to tackle long-lived gases released at the surface, not short-lived pollutants injected directly into the stratosphere. That leaves a policy gap. If the industry keeps growing without oversight, rocket pollution could undo some of the gains we've fought so hard for. But if scientists, policymakers, and space companies work together now, the space age doesn't have to come at the expense of the ozone layer. Today, the impact of rockets on ozone is still relatively small compared to the damage caused by CFCs in the late 20th century. But the trajectory is clear. What seems small now could become significant tomorrow. The ozone layer is one of Earth's most vital natural shields, and it is finally healing after decades of effort. Whether it continues to recover, or whether that recovery is stalled by the rise of rockets and satellites, depends on the choices we make today. So as we cheer every new launch and marvel at the possibilities of space, we need to remember, our reach for the stars must not come at the cost of the protective veil that makes life on Earth possible. The ozone layer saved us once. The question is, will we save it again?